Exercise 1822 is trying to get you to turn isopropyl benzene into acetophenone right here. And so whenever you do these syntheses, you can see first that the place where things are changing is at the benzylic position. You've got that, whenever you see a benzene molecule, you'd think, okay, the rings are really stable. Unless I use special tricks to make stuff react with that, most of the which you would learn, and you'd learn the special tricks in chapter 19, then any of the other reactions you've learned before chapter 19, those reactions are going to tend to not react with that ring. Where they will react is at the benzylic position, which is very reactive because you can form high energy intermediates like carbocations or lone pairs with negative charges, or even radicals, unpaired electrons. You can form those at that position, and because it's allylic to the pi bonds in the ring, it's stabilized through all of that parallel p orbital system all over that ring. So those unstable species are able to bleed into those parallel p orbitals so that they help to stabilize the charge there. So the benzylic position is really reactive. And we can use those reactions to create the transformation that's happening here, which clearly has something to do with the benzylic position. So the first step usually when you look at these syntheses is to see if the number of carbons change, because there aren't very many ways to change the number of carbons on a molecule. You can add them, like with Grignard reagents or with Diels-Alder reactions. But in this case, if you count the number of carbons, you have the 6 in the benzene, that stays the same, and then you have 3 in the reactants, but in the products you only have 2 carbons. One of the carbons gets replaced by an oxygen. So you're decreasing the number of carbons. So you're not adding carbons. That means you don't want to have a carbon nucleophile. So we definitely wouldn't do a Diels-Alder reaction. We're not making a ring. And you wouldn't even use a Grignard reagent because that would increase the number of carbons on the molecule. So instead, here we need a way to chop or saw carbons off of this molecule. Now there is one way you can do that at the benzylic position, but it's brutal. You can treat this, any benzylic position that has a hydrogen, and this does, any benzylic position that has a hydrogen will react with strong oxidizing agents, like sodium dichromate in sulfuric acid and water, or sometimes they'll just give you chromic acid. You can use strong oxidizing agents like that, or like KMNO4, potassium permanganate. And those will just turn any benzylic position that has a hydrogen on it into a carboxylic acid. Notice, though, that that is too violent of a procedure for what we want. If we do that, we would just get benzoic acid. And as of right now, we haven't learned how to change a or interact with a carboxylic acid functional group. That will happen, we'll learn how to do that in a future chapter. But for right now, we would sort of be at a dead end here. We wouldn't know how to turn that carboxylic acid into this ketone. So that is maybe not a good idea for us at this point. In a future chapter, when we know how to manipulate carboxylic acids, that might be a viable option. But for right now, these strong oxidizing agents are not going to work because they would give us benzoic acid, they would give us a carboxylic acid, when what we want is a ketone. They would take too many of the carbons off. They would take 2 of them off. We only want 1 of them off. You might remember from Organic Chemistry 1 that there's another way that you can saw off carbons, and that's using ozonolysis. If you remember, if you have a double bond between carbons and you treat it with ozone, so O3, followed by dimethyl sulfide, DMS, that saws that double bond in 2. And what you end up getting are the 2 pieces. So here I'm going to draw those 2 pieces separately. you get those two pieces with double bonds to oxygen instead of to the carbons, to each other. So in this case, if I were to draw this in a way that looked a little less weird, you would have acetaldehyde, it's the molecule on the left, and you would have formaldehyde, the molecule on the right, in this particular reaction. So the mechanism for that was a little complicated, and I would encourage you to go back and review that from Organic Chemistry 1, the video for that, to see the mechanism for how that happens. But that's the effect of adding ozone followed by dimethyl sulfide, DMS. So, if we were somehow to turn this carbon-to-carbon bond into a double bond, then we could react it with ozone. We could do ozonolysis, react it with ozone and dimethyl sulfide, and that double bond would turn from a double bond to a carbon to a double bond to an oxygen. So there's our strategy. We're going to try to get a double bond here. Once we have that, we can do ozonolysis to replace it with a double bond to an oxygen. But how do you get a double bond? You create double bonds with elimination reactions. And to do elimination reactions, you need a leaving group. Elimination reactions have two sort of curved arrow patterns in them. They have proton transfer and loss of a leaving group. So you need a leaving group on the molecule. So the first step is to put a leaving group onto that molecule. And we've seen this in exercise 1821. Halogens are the gateway to so many other reactions. And we can put a halogen on that benzylic position using N-bromo-succinimide, NBS, and heat. N-bromo-succinimide is that molecule, looks like this. And if you heat it up enough, or if you shine light on it, that bond breaks homolytically and you end up getting two radicals. The bromine radical ends up stealing the hydrogen off there, forming a radical there, and a second bromine radical swoops in and combines with the radical that you formed on that carbon. So if you're unsure about that mechanism, go back to the video for 1821 and you'll see that mechanism there in that video. The result is that on that benzylic position, you'll now have a bromine. That's the effect of treating that with NBS and heat, radical halogenation. Well, now we have a leaving group. We have a great leaving group, a halogen, and so we can definitely do elimination. When you do substitution, you add a nucleophile. When you do elimination, you add a base. The bases are usually alkoxides, so some carbon chain with an oxygen on the end that has 3 lone pairs and a negative charge. The conjugate bases of alcohols, alkoxides. There were 2 alkoxides that you saw a lot in Organic Chemistry 1. One was ethoxide, so eth, and then oxide, eth because 2 carbons. And another one we talked about in the video for 1821, that was tert-butoxide. So you had tert-butyl group, and then oxide. Usually you would add these as salts, so it would be something like sodium ethoxide or potassium tert-butoxide. And what the counter ion is with the positive charge doesn't really matter. You could switch these around. You could have potassium ethoxide if you wanted to, and sodium tert-butoxide if you wanted to. So you could treat it with either of these bases just for the sake of variety. Since we used potassium tert-butoxide last time, I'll use sodium ethoxide this time. So you can treat this with sodium ethoxide, and the negative charge there is going to steal one of those beta hydrogens. So the halogen is attached to the place where the halogen is attached, that's the alpha carbon. Right next door is the beta carbon, and all the hydrogens on that beta carbon are beta hydrogens. So that base is going to steal the beta hydrogen. The electrons will go toward the leaving group, kick the leaving group off, and what you end up with is the double bond, the elimination product. So, I'm just going to erase these. That's the mechanism for how it's happening. The mechanism for how it's happening. But just so we can see the progression, the narrative, I'm going to erase those. So by treating this halogenated compound with sodium ethoxide, NaOET, this is just those two carbons, CH2CH3, with the oxygen on them, negative charge on that, balance that with the positive charge on the sodium, you'd create that elimination product. You'd create that double bond. And once you have that double bond, you can saw it off, you can saw it apart like we saw with ozonolysis. So if you were to treat that with ozone, followed by dimethyl sulfide, you'd end up with two products. First, the product that we always wanted, and second, you would also have, formaldehyde. That's what that top part would turn into. So when you do ozonolysis, you draw that red line in between the double bond. You draw each of the pieces separately, so this whole thing, that's this at the bottom. And then the other side of that squiggly red line, you have this, that's this here. And then instead of having the double bond between the two carbons, you have the double bond between the oxygens, going to the oxygens. And that was the product we wanted, right? That was our beautiful acetophenone. There. So, as we often do, we used NBS, N-bromosuccinimide, in heat to put a halogen on that benzylic position. And once you have that, we have the gateways open. We can do substitution, elimination. Here, we wanted to do elimination to form a double bond. So we added a base. We used a skinny base, sodium ethoxide. Could have used potassium tert-butoxide, a bulky base if we wanted to. That gave us an elimination product with an extra double bond. And once you have that double bond, you can use ozone and DMS to saw it apart. And that would give us formaldehyde, which we really don't care about, and acetophenone, which is what we wanted the whole time.